Welcome students. I am Rekha Thorat, Associate Professor. Today we consider some theorems on groups for homomorphism and some cyclic subgroups of group G. Let us consider theorem number 4. Let F is from G to G dash be a homomorphism defined from a group G into group G dash and H be a subgroup of group G. Then f of H is a subgroup of G dash. In the proof, we assume that F is from G to G dash be a homomorphism defined from a group G into group G dash. Let H be a subgroup of group G. Then f of H equal to set of all fx belongs to G dash such that x belongs to G. Since f is a homomorphism, therefore f of E equal to E dash where E belongs to H, which implies that E dash belongs to f of H. Hence, fH is 1 non-empty subset of G dash. Now let f of A comma f of B belongs to fH. Then f of A into in bracket f of B bracket complete inverse equal to f of A into f of B inverse by theorem number 1 of second property, which is equal to f of AB inverse since f is an homomorphism. Now A comma B belongs to H, and since H is abelian group, H is a group, therefore A comma B belongs to H implies AB inverse belongs to H, and this implies f of A into in bracket f of B inverse belongs to f of H. Thus f of A comma f of B belongs to f of H implies f of A into f of B inverse belongs to f of H. Hence fH is a subgroup of G dash. Thus f is from G to G dash is homomorphism defined from a group G into group G dash. Then H is a subgroup of G. That means if H is subgroup of G, then f of H is a subgroup of G dash. Now we consider next theorem, that is theorem number 5. Statement of this theorem is let f is from G to G dash be a homomorphism defined from a group G into itself and H be a cyclic subgroup of G. Then fH is cyclic subgroup of G. In the proof, we assume that f is from G to G be a homomorphism and H be a cyclic subgroup of group G generated by A. Then H equal to set of all x belongs to G such that x equal to A raised to n, since H is cyclic subgroup generated by A, so that x equal to A raised to n, and H is cyclic group, so that H equal to set of all x belongs to G satisfying the property x equal to A raised to n, where A belongs to G and n belongs to Z. Now fH equal to set of all fx belongs to G such that x belongs to G. Then by previous theorem f of H is a subgroup of G. Let x belongs to f of H. Then x equal to fH for small h belongs to capital H. But h belongs to H implies h equal to a raised to m for some m belongs to Z, since H is a cyclic group, so that h belongs to H implies h equal to a raised to m for m belongs to Z. Hence, x equal to fh implies x equal to f of f into bracket a dot a m times bracket complete. This implies x equal to f of a dot up to f of a m times, since f is homomorphism. This implies x equal to in bracket f of a bracket complete raised to m. Thus, x belongs to fh implies x equal to in bracket f of a bracket complete raised to m for some m belongs to Z. Hence, fh is a cyclic subgroup of G. Now we consider one definition. Definition of kernel of homomorphism. Let f is from G to G dash be a homomorphism where G and G dash are two groups. Then kernel of f is denoted by kernel of f and is defined by kernel of f equal to set of all x belongs to G such that f of x equal to e dash, where e dash is the identity element of G dash. These definitions can be considered for objective also. That is, if f from G to G dash is homomorphism, where G and G dash are two groups, then kernel of f equal to dash dash. That is, set of all x belongs to G such that fx equal to e dash. Or this can be asked in another way as, if G and G dash are two groups and f is from G to G dash be a homomorphism, then the set x belongs to G satisfying the property f of x equal to e dash equal to dash dash equal to kernel of f. Now we consider next theorem. Number 6. Statement of this theorem is, if f is from G to G dash is a homomorphism, then kernel of f is a normal subgroup of G. For objective, the statements of theorems can be asked. For example, if f is from G to G dash is a homomorphism, then kernel of f is dash dash of fg, normal subgroup of fg. Or if f is from G to G dash is a homomorphism, then dash dash is a normal subgroup of G. Kernel of f is a normal subgroup of G for objective. Let us consider the proof of this theorem. Let f is from G to G dash be a homomorphism. Then kernel of f equal to set of all x belongs to G such that fx equal to e dash, where e dash is the identity element of G dash. Since f is a homomorphism, f of e equal to e dash, e belongs to kernel of f. Therefore, kernel of f is non-empty subset of G. Let x comma y belongs to kernel of f. Then x comma y belongs to kernel f implies fx equal to e dash and fy equal to e dash. Consider f in bracket xy inverse bracket complete equal to f of x into f of y inverse, since f is an homomorphism. Hence, f of xy inverse equal to f of x into f of y inverse by theorem number 1, which is equal to e into e dash equal to e dash, since e is an identity. Thus, f of xy inverse equal to e dash. Therefore, xy inverse belongs to kernel F for all xy belongs to kernel F. Hence, kernel of F is a subgroup of G. Now let G belongs to G and X belongs to kernel F. Then f of G inverse xg equal to f of G inverse into fx into fg, since f is an homomorphism. Hence, f of G xg inverse equal to f of G inverse into fx into fg by theorem number 1, which is equal to f of G inverse into a dash into fg, since f of x equal to a dash. Thus, f of G inverse xg equal to f of G inverse into fg. Thus, f of G inverse xg equal to a dash, since f of G into f of G inverse equal to a dash. Thus, we get f of G inverse xg equal to a dash. Therefore, G inverse xg belongs to kernel F for all G belongs to G and X belongs to kernel F. Hence, that is f of G inverse xg equal to a dash. Therefore, G inverse xg belongs to kernel F for all G belongs to G and X belongs to kernel F. Hence, kernel F is a normal subgroup of group G. Now we consider one theorem number 7. A homomorphism f from G to G dash is 1 1 if and only if kernel of f equal to singleton E, where E is the identity element of G. In the proof, we assume that f is from G to G dash be a homomorphism. Let f be 1 1. To prove that kernel of f equal to singleton E, let x belongs to kernel of f. Then f of x equal to E dash by definition. Now, as f is homomorphism, f of E equal to E dash. Thus, f of x equal to E dash and f of E equal to E dash. Therefore, f of x equal to f of E. But f is 1 1. Therefore, f of x equal to f of E implies x equal to E implies x belongs to singleton E. Thus, x belongs to kernel F implies x belongs to singleton E. Hence, kernel of F is subset of singleton E. Denote it as number 1. Again, E belongs to singleton E and f of E equal to E dash implies E belongs to kernel F. Thus, x belongs to singleton E implies x belongs to kernel F. That means singleton E is subset of kernel F. Denote it as number 2. From 1 and 2 we get kernel of F. From 1 and 2 we get kernel of F equal to singleton E. Conversely, let kernel of F equal to singleton E. We have to prove that F is 1 1. To prove this, let fx equal to f of y. Then fx equal to f of y implies f of x into fy inverse equal to a dash. And this implies f of x into fy inverse equal to a dash by theorem number 1. This implies f of xy inverse equal to a dash since f is an homomorphism. Therefore, xy inverse belongs to kernel of f, since f of xy inverse equal to a dash. But kernel of f equal to singleton E. Therefore, xy inverse belongs to singleton E, as xy inverse belongs to kernel f. Thus, xy inverse equal to singleton E implies xy inverse equal to E, and this implies x equal to y. Thus, fx equal to fy implies x equal to y. Hence, f is 1 1. Thus, F is a homomorphism from a group G onto group G dash, which is 1 1. Thank you.